Hello students, welcome to Inside Physics. Today we are going to discuss about extrinsic semiconductors. We know what is a semiconductors. These are materials which have a conductivity in between the conductors and insulators. Based on resistivity also, the materials like metals are divided into three categories: insulators, conductors and semiconductors. Why the semiconducting materials have that much importance means they are widely used in electrical and electronic circuits and devices because they have high resilience to the temperature. That means the resistivity, the resistance of the semiconducting materials will not increase as per the regular conductors do by increasing the temperature. That means, see, with the increase of temperature, the resistivity of the semiconducting materials will decrease actually with increase of temperatures. So these materials are widely used in electronic devices. Here we classify semiconductors into two types: elemental and compound semiconductors. In elemental type, the widely used materials are silicon and germanium with their tetravalent valency. So these are the two elemental materials which are in wide use. So based on their uh, impurities or based on their uh, chemical nature, they are divided into intrinsic and extrinsic semiconductors. So here we discuss how the extrinsic semiconductors are made from the intrinsic semiconductors. Intrinsic means chemically pure. There will not be any impurity and they are as it is and they are pure in elemental form. Okay. So extrinsic semiconductors. So why we require extrinsic, that means impure? When a pure semiconductor is added with some impurity, what is the impurity that is being added, we will discuss in this session. See, why we need to add an impurity to the intrinsic semiconductors? Because we need to increase the conductivity of semiconductors. We cannot use a chemically pure semiconductor as it is in electronic devices, because at room temperature the conductivity of semiconducting materials is very low. We need more conductivity, that means high conductivity, so that they can be used in electronic circuits. That's why we add an impurity to the chemically pure or intrinsic semiconductors, and when an impurity is added, that means the addition of impurity is called doping. The process is called doping, and when we dope an intrinsic semiconductors with some impurities, then it is transformed to extrinsic semiconductor. So in this we have further two types, N type and P type semiconductors. Before going to that categories, see what is the doping element, that means the dopant, the impurity, and how we need to take an impurity to add to the semiconductor materials means, generally the used materials already I have said silicon and germanium, as they are tetravalent. So when we add an impurity to these tetravalent atoms, and their atomic structure should not be disturbed because of the impurity. So the impurity atom that we are going to select to add to these elemental semiconductors must be of the same size or nearly of the same size with these silicon and germanium atoms, so that the atomic structure, the lattice, will not be disturbed by adding the impurity atom, and if the atomic size is nearly same, uh, the addition of impurity atom is also having the same atomic size or nearly the same size, then there is no disturbance in the lattice. That is, the lattice means the regular arrangement of atoms. So that is why, see, the elements silicon, germanium belong to fourth group in the periodic table. So if you can select the elements from what is the nearest group to the fourth group, that is fifth or third. So if you can select an atom from fifth or third group, so that will be almost nearly equal to the atomic size of the fourth group elements. So we have here two types of impurities. Those are pentavalent and trivalent impurities. The impurities that we select are of pentavalent valency and trivalent valency. So pentavalence means in the outer orbit, the element has 5 electrons, and this is trivalent valency means the outer orbit of an atom will be having 3 electrons. And for pentavalent, we have the examples like arsenic, antimony, and we have phosphorus. So these are the examples for pentavalent valence atoms. And in trivalent category, we have aluminum, boron, and indium. So, and see, we can take an element from this category or this category, and we can add to the elemental semiconducting materials, that means intrinsic semiconductors. Then by the addition of impurity, they are being converted into two further categories. Those are: one, N type semiconductors; second one, P type semiconductors. So we will discuss the doping process, how the material will be affected by doping with the pentavalent atom and or trivalent impurity. So if you add the material with pentavalent impurity, so the element will be converted into N-type semiconductor. If you add trivalent impurity to the semiconducting material, it will be converted into P-type semiconductors. So what is the difference between N-type and P-type means? In N-type, the majority charge carriers are electrons. So in P-type, the majority charge carriers are holes. So we will discuss what are actually, how the majority will be electrons in N-type and how the majority will become the holes in P-type. Okay, so we'll take up first the N-type semiconductors and how the doping will be done in N-type materials. So here we add a pentavalent impurity to the silicon material. So the atomic structure will become, see, this is a silicon lattice, and we have a pentavalent atom at the center. So if it has 5 electrons in the outer orbit, so it shares in the bonding with the silicon atom, it shares 4 outer electrons with 4 silicon atoms and one more electron which is excess in the donor atom, that is dopant atom, will be held very weakly to the parent atom, and other 4 electrons are shared with the other 4 neighbor silicon atoms, which is a tetravalent atom. Okay, but the excess electron which is there in the outer orbit of the parent, that's dopant atom, will be very weakly bound to the parent atom. That means weakly bound means the ionization energy, it can be easily removed with the low ionization energy. That means even it can be made free with at room temperature also. So here the excess electron will be participating in the charge carrying process. Okay, here the intrinsic carriers, that means intrinsic means the silicon atoms, even if we have these silicon atoms are also contributing the intrinsic carriers concentration. That is, see, for this silicon and germanium atoms, this electron is weakly bound to the parent atom, and that can be removed by giving a small amount of energy like 0.01 electron volts for germanium atom and 0.05 electron volts for silicon atom. I am talking about the fifth electron regarding this donor atom. Okay, so this is for extrinsic carriers. That means the electrons, one electron, excess electron is the extrinsic carrier. In the intrinsic category, the silicon atom also will be generating some excess electron, the free electrons, by giving some energy to it, and the energy that can be given to the germanium atom is 0.75 electron volts. In case of germanium atom, it is 1.1 electron volts in case of silicon atom. Okay, so compared to these energies, the ionization energy of the fifth electron is very low. So this electron will participate in the carrier as a carrier of charge, that means in conducting electricity easily than the intrinsic carriers. So if an intrinsic electron from the silicon atom is removed from this silicon atom, then there will be a hole generated in place of the in the parent atom. Okay, so when an electron is removed from silicon as an intrinsic charge carrier, there is a vacancy for electron, that is called hole, is created. Okay, so with the impurity is being added as in parts per million. How we add the impurity? It will be, the unit will be parts per million, ppm, we call it ppm. So when we increase the parts per million, the impurity level, so the number of electrons from the donor atom will increase, and the holes created by the silicon atoms with the intrinsic charge carriers being removed from the silicon atom will be made to occupy by these electrons from the donor atom. The free electrons will be occupying the holes, and the holes are being collapsed by the electrons. So here the only majority carriers will be electrons, and the intrinsically generated holes will be occupied by the extra fifth electron, and thereby all the holes generated intrinsically will be occupied by the electrons. So the minority carriers will be holes and the majority carriers will be electrons. If you want to increase the conductivity furthermore, we need to increase the impurity atoms level. then we will get more conductivity in the silicon material. So this will be like n-type materials where the charge carriers are electrons, majority charge carriers are electrons. So we will see what happens in the p-type, how the holes will be the majority carriers in p-type materials. So p-type semiconductors means if you add a trivalent impurity to, suppose like silicon or germanium, again we take the same structure here, and in the middle we have a trivalent atom which is contributing its 3 valency electrons with the bonding with silicon atom. So if it is having a trivalent atom means like aluminum, boron or indium. So if it is having only 3 electrons in the outer orbit and it can share only 3 electrons for the bonding with silicon, neighbor silicon atom. So there is a hole created in the bonding. There is a hole created in the bonding with the silicon atom for this trivalent impurity atom. So if every impurity atom creates a hole in the bonding with the silicon atom. So these holes are additional to the intrinsically generated holes where the silicon atoms also generates the intrinsically generated electrons, and these holes are added to the number of holes that are being added intrinsically. Here see, these holes and the additional holes generated by silicon atoms will be the majority charge carriers. So what about the electrons that are being liberated from the silicon atom? That means the intrinsic carriers of charge. So they also encounter the holes, and the holes are being occupied by the electrons. So the hole is being collapsed. But here the impurity atoms will be more and the number of holes is more compared to the intrinsic electrons liberated from the silicon atoms. So even they encounter these holes, some of the electrons, so the electron number will be less than the holes because of the more number of holes are there, and the impurity is creating the holes more than the electrons. So in this way holes are the majority carriers, and if you can observe, see this hole is occupied and by an electron which is coming from the other silicon atom, and it occupies here. Suppose we have another silicon atom at some distance, and if you give some ionization energy to this material, like after adding the impurity, the electron from the silicon atom will be occupying and coming and occupying this hole to abolish this, nullify this hole. So then what happens? A hole is being created in this, at the silicon atom, in this silicon atom, and the conduction of electricity now is being done with this hole participation, and holes are here the majority charge carriers. In the same way, the hole created here will be occupied by some other electron which is in the neighborhood from the silicon atom, and here the whole movement will create the electricity charge flow in the materials, and these type of materials are called p-type materials. Okay, so this is how we can have an explanation for n-type and p-type semiconducting materials. Okay, So after this session we will see how the energy levels of a semiconducting materials is being affected after the impurities are added. So that we will see in the next session. Okay.